We are, it's time for our second talk. I'm delighted that we are having Carola Schönlieb as our second speakers. This time, one advantage of Zoom, you didn't have to travel, right, all the way from Cambridge. So I will hand it over to Carola right now, who will be talking about learned adversarial regularizers. Please.
Okay, thanks a lot, Dejan. Although I'm not sure if it's such an advantage. I have to say I'm really missing the travel and really person interaction. But thanks a lot for organizing this, because this comes close to this. So we have some replacement for our usual workshops. So thanks a lot for organizing and also for inviting me. Thank you. Okay, so let me just dive into this straight away. So before I start, let me just really give credit to the research group that I'm working with here in Cambridge, without whom this would really not be possible. And many of these people that you see here have in particular contributed to what I'm going to discuss today. So thanks a lot to them. And then, of course, also thanks a lot to all the funding that is supporting us, which, again, it would not be possible without that. So what I want to discuss with you today is the idea or a strategy for learning regularizers that can be used to solve ill-posed inverse problems, in particular inverse problems in imaging. And I want to discuss this idea of learning such a regularizer in an adversarial way, and this will become clearer soon what this exactly means. But that's where the name comes from. So a few messages that I want to convey along the way. Can you see, by the way, my mouse? My little hand, do you see that moving? Yes, okay, thank you, Dejan. So the first one, the first message is, I really believe that deep learning offers a very interesting opportunity for solving inverse problems, just bluntly, really, because of what is written here in parentheses, that deep neural networks have such strong approximation power that they can help us to be very, very adaptive to the data. And that can be bad on the one hand, but if you do it well, it also can work for you. The interesting thing for us is that deep learning off the shelf does not work for ill-posed inverse problems. And with that doesn't work, what I mean is it doesn't work reliably, it doesn't work robustly. All these things that we need to make sure when we solve inverse problems, that they hold. We can't be sure that they hold with just neural networks. With just neural networks alone. So what we need is a combination of using deep learning together with mathematical and statistical modeling. And what I will talk about today is, what I want to show you is that we can do that by using as the mathematical framework variational regularization problems, or variational regularization approaches, and then use the neural network to make the regularizer data adaptive, to learn the regularizer, and keep the rest of our nice mathematical framework and also kind of statistically motivated framework intact. So that's roughly the idea, and we'll get there in a moment. So very briefly, the type of inverse problems that we are looking at are inverse imaging problems, where if we start with the bottom line here on the slide, what we are measuring is little y, that you can just throughout the talk, just imagine y and also the quantity that you want to reconstruct from y, which I call here little u, live in normed vector spaces. These will actually only, I think in this talk, I only consider Banach spaces. So these, you can just think of Banach spaces. And what the problem in inverse problems is that measuring Y, which is a noisy version of transform measurements of U, you want to reconstruct U. And capital T could be linear, could be non-linear. That again depends on your application. But capital T measures basically the process that your quantity U, which in inverse imaging in a lot of cases is an image or some information that is hidden in an image, that U has gone through before you observe it. So in this example that I have here on the top is an example you can keep in mind, because it's also the example I show you in the experiments for the adversarial regularizer. This is the example of X-ray tomography or computer tomography. So here the measurements Y look like this. So these are also called sinogram measurements. These are basically what you can think of is the accumulated attenuated energy that an X-ray is experiencing when it travels through your body, that is being measured at different angles and at different y-intercepts. So this parametrization here is angular, and then also the line discretization. So the number of parallel lines at a particular angle that are shot through your body. And so what is plotted here, you can think of in mathematical terms, is a line integral of U. So a line integral over the density U, where the density is the tissue density that is the cause for attenuation of the X-rays. So capital T in this case is the radon or X-ray transform, and U is an image that looks something like that. Yeah? So this is an abdominal scan where you see a slice through the lungs. Okay. And there are many, many more examples of this kind. Medical imaging is, of course, a very prominent one. We just heard about CT, but there are many, many others: MRI, PET, electrical impedance tomography, lots of different inverse problems in this regime. Non-destructive testing is, of course, another one when you want to understand material properties without cutting objects open, but you want to look through them. Remote sensing is another one. So where you look at, for instance, material properties or 3D geometries of the ground, of objects that are on the ground from above, to do quantification analysis on a large scale. So either from satellites or from airplanes or something like that. And another one that I'm putting here, just because my research group is also working a lot on these type of problems, and these are sometimes maybe not so much counted towards this classical idea of inverse problems, are problems in computer vision and image analysis. So here, writing down the capital T, this forward operator, is not straightforward, of course, but again, you follow the same principle that you have measurements, which in this case are either images or videos, and you want to extract information from these that are hidden in them. So like a segmentation or a classification, or yeah, so there are many more examples. So why these problems are so tremendously difficult to solve, even if you're starting with a linear and bounded operator, capital T, is that they're ill-posed in the sense that this capital T is not invertible or has an unbounded or discontinuous inverse. And examples for such forward operators are compact forward operators with infinite range. In imaging, what also very often happens is that you are not measuring as much as you need to determine your degrees of freedom, which are usually, let's say for CT image reconstruction, the number of pixels or voxels in your CT image or volume. So there is this conundrum usually with very high resolution reconstructions that you want to compute because you want to see something. You want a high resolution model of what is happening inside the body, but on the other hand, in CT you don't want to radiate the patient too much, which usually results in a low dose scan, which then gives you lots of noise, and then and as well sometimes that you don't fully sample angularly, but you do a sparse. Your discretization in the angular direction is quite sparse. And then there are also other examples. We actually get to them. I shouldn't talk too much about it. But underdetermined data is another big reason why this is a problem. Underdetermined data coupled with the problem of noise. And the consequences are instabilities, non-uniqueness, and so on. And so these instabilities in particular, to not have this property that the solution continuously depends on the input, is something that that is bothering us and that we want to that we want to correct, so that we need approaches that guarantee that. Okay, so one approach that I want to connect my learning idea with is the variational regularization approach. And so here, again, I'm starting with my measurement model. So my measurements are y, and what I want to reconstruct is little u. And so one way to get around the ill-postness of this, meaning that I can't just invert this capital T, is to phrase the problem or to compute an approximation to this equation here as a minimizer of a functional that on the one hand measures closeness to my measurement model. So I'm looking for a minimizer of this functional that consists on the one hand of a distance term between the forward model and the measurements. And think of this in the simplest case, and in a lot of cases here, actually also in what I'm going to show you, lots of inverse imaging problems have that, is this L2 squared fit between your forward operator applied to u and y. And sorry, by the way, I'm sometimes switching between linear and non-linear notation. So at the moment, everything could still be non-linear, by the way. Yeah? So there should be parentheses here. Okay, so this is my data fidelity term, and then the other one is the one that should somehow take care now of the ill-postness by regularizing the problem, by kind of narrowing down your search space for a u that fulfills my measurement model by saying, I know something else about you, not only that it's close to y, but I also know that it has this particular regularity. And so in image processing, a regularity that that had a huge effect over many, many years since, I would say, the seminal paper of Rudin, Osher, and Fatemi in the 90s, or Chambol and Lyons as well, is this idea of total variation regularization, where you say that a good representation of the type of images U that I want to reconstruct are functions of bounded variations. There's a good function space we want to be in. And the total variation in particular minimizes U of this functional to be discontinuous, so to have edges which are something that turns out is something both visually but also quantitatively super important to preserve. And then on the other hand, attenuate all the noise and corruptions that we get from these random corruptions that the data is that the data is equipped with that attenuates this noise, these small oscillations, because the total variation would be very large for that. So this is one way to think about it. The other way is to think about it in terms of sparsity. This is a sparsity promoting regularizer that says that the gradient of the reconstruction should be 0 in almost all places and just non-zero in a few characteristic places. And these characteristic places should be the edges. So that you could think of the typical TV total variation type reconstructions looking piecewise constant. And then there is the little alpha, which balances this regularization against sticking to the forward model. Okay, so this is the framework. So a long explanation for the framework. So this is the variational approach that I now want to play around with a little bit. And just to motivate this, let me show you a bit what people have already thought about in terms of regularization. So the total variation is one example, and I'm putting this here on the first slide because this has been an example that has been super successful in not just in mathematics, but in lots of applications where imaging has been used. But there are many more examples that are descendants or kind of have been developed in parallel to this total variation idea. One of them is, of course, that many of you know is multi-resolution analysis, wavelets, other Banach space norms, Sobolev norms, Besov norms, versions of total variation like higher order versions, so with higher order derivatives, or non-local versions, anisotropic versions, so not just the nonlinear regularization, but also one that gives you a directionality, and so on and so forth. So there has been a lot of development here, and this list could go on. There are lots of developments. And so with this list, maybe you also see on the one hand how successful this idea of regularization has been, because it really allows you to model the type of solutions that you want to reconstruct from your measurements. Why? And it also allows you to do this in a mathematically well-posed way. But you also see that it's not just one regularization that fits all, but this regularization, there are various different approaches that have been developed for different types of images, let's say. And the common denominator in all of them really, I would say, is that has been the trend that has been most successful is this idea of sparsity, that actually, or sparsity in terms of also the relevant geometrical features that are important to model images in general, or to represent them well. So I told you that total variation has been super successful with image processing, but then I also told you that it basically says images are piecewise constant. So how does this fit together? How can such a simple model be so successful? But it has been. So this is the kind of overarching idea. And just to give you one quick example of that. So what you see here is a simulated computed tomography example, where on the left, you see the ground truth, which is a high dose, full angle CT measurement. Okay. And this is a little zoom of it. And then what we did, or what Shubo did, was that he simulated a sparse angle, meaning that you discretize very coarsely, angularly, along the angles, the angular dimensions, you sample coarsely, and you put noise to the measurements and so on, and then you reconstruct via what is called filtered back projection, or what you can also think of as is a minimal norm solution, where you basically minimize the L2 squared fit to the data, plus an L2 norm constraint. So that is what you get when you do this, which is basically kind of you can think of as the bottom line unregularized reconstruction. So you see what the problem is, you get noise, you get lots of these artifacts, these streak artifacts that come from the undersampling in your measurements. Now, if you do this with a total variation, you immediately see a clearer picture. So if I go back and forth, I mean, for people who have seen this before, this is kind of an old hat, right? But for people who haven't seen this, I think this is kind of super impressive. So by regularizing the problem, and you can argue whether this is the right way to regularize or not, you actually get really something where you can also see, if you look at the zoom here, you can also see that the important things that should be highlighted are highlighted, and that things that are kind of in the background are kind of attenuated. Yeah. Okay, so this is maybe still arguably we could maybe do better, and so this talk is about how you might be able to do better. And so yeah, so even I could show you lots of more pictures with all these regularizers here, but I won't. What I do is I now go to the learning. So the idea is, in this presence of these various different approaches for regularizing variational inversion, maybe can we also think about using the data itself to help us build regularizers? Okay, so this is somehow the idea. And I think really going back to my main message, all of this will not work if you just go ahead and use a neural network to do the job. What the situation is that I want to be in here is that I want to start I want to take as a starting point what we already know that we can do well and that we like. So I want to start with this idea that I have variational methods. I know something about the associated regularization effects that I can analyze, for instance, by analyzing nonlinear PDEs and so on. So I know qualitatively also about some of these things. I can use functional analysis. I can use numerical analysis. I can use optimization. I can use statistics also to understand solutions. And I want to use learning only to complement what I cannot model well. This is roughly the idea, yeah? And this, on the one hand, allows you to at least hope that you might be in a regime where you can still prove something about this kind of hybrid model between learning and modeling. But also, and this might also make sense intuitively, if you only parameterize the things that you can't model well and then make them, then learn them from the data, the number of parameters you need in order to do this is much smaller, as if you would solve your problem in the first instance by a neural network, yeah, without forgetting about the modeling. So this also means that this is something that should work in regimes where I don't have a lot of labeled data available necessarily. Okay. And the other message is, because I'm sticking to a variational model, I don't want to learn how to reconstruct, because I want to reconstruct with my variational approach. I want to learn the prior, right? I want to learn the kind of things that images I want to get, that images I want to see as solutions of my variation problem, of what they are kind of made of. So this is somehow the idea. Okay, and this reaches the adversarial regularizers, and this is joint work with a number of people. The ones who are here highlighted in red are the ones I didn't find a picture of. So very sorry for that. So Søren is he just had his PhD examination last week. Søren was a PhD student of Peter Maas in Bremen. Sebastian Lunz, who is this guy here, is a PhD student of myself in Cambridge. Shubho Mukherjee, who is here, is a postdoc who just started with me a month ago and was before with Ozan Öktem at KTH. And then Zach Shumyanov is one of these students that you meet almost only once in your lifetime or so, who worked with us after having done math undergraduates after having done, he worked with us on this after having just finished 1 year of math undergraduate. And then he did what you will see now. So this was super amazing. Yeah. Okay, so what's the framework I want to learn in? So now I'm becoming a bit more modest. Before I said this capital T could be linear or non-linear. So now I'm going to look at linear and bounded forward operators, capital T. And I look at two Banach spaces, X and Y. One is for the measurements Y, and the other one is the one I'm minimizing over. So this is the Banach space where my reconstructions should lie in. So this is X. And there are lots of reasons, again, why I want to stick to this variational approach in the learning framework. Well, because what I'm going to learn will be in a kind of very explicit fashion, will act as a prior or a regularizer or something at least that should describe the type of images I want to reconstruct. I can prove things about this variational approach, even if I'm going to learn my regularizer, and I'm going to show this in a moment. I can use the regularization parameter also to adapt to the noise level. And also, I have actually, now talking about the noise, I can also incorporate the distribution of the data, the distribution of the noise very explicitly in how I choose the data fidelity, the data discrepancy term here. And I have my forward operator. This is also a super important reason that my forward operator, I always keep when I'm looking for solutions U. So the only thing really I want to learn is the regularizer. All of the other stuff I'm keeping. Okay, so this is just what I said. I want to learn now this regularizer. So when you start thinking about learning something, you look what other people have done. And so here are just a few examples of what conceptually what people have done to learn regularizers. So one maybe of the most prominent approaches that people have done, in particular, actually more in signal processing, not so much with the actual forward operator in mind, more for things like image decomposition or image denoising or things like this, is this idea of sparse coding and dictionary learning. Okay, so here the idea is actually going back again to this sparsity promoting regularization that we had before in terms of the total variation. Now we say, I don't know what my sparsity promoting representation of the image is. I know that I want a sparse representation, but I don't know the elements or the expansion, the basis elements that my image should be sparse in. So what these dictionary learning people are doing is they write down the solution to this minimization problem as a linear combination of basis elements phi I with coefficients gamma I, where they have a sparsity constraint on this gamma vector. And then they are not just so sparse reconstruction would just be I fix the phi's and then I reconstruct, but here you're also learning the phi's. Okay, so this is dictionary learning. There are lots of examples where people have looked at this. Another thing that I found kind of interesting and that actually was very prominently acknowledged as a contribution to the imaging society as a whole this summer, at the SIAM Imaging Conference, because it actually got 2 awards from the SIAM Imaging Activity Group, was this idea of plug and play, of a plug and play prior or regularization by denoising. So here, the idea is without explaining exactly why this parameterization. So you start again with a variational regularization approach. You parameterize your regularizer in this way. And then you take as your lambda an off-the-shelf denoiser. Okay, so any any super duper image denoiser that people have developed, BM3D or your favorite neural network or whatever, you take that and you plug it into that, and then you solve your inverse problem in this case. So you use a denoiser to regularize. Basically, this is here the idea. And I'm very sloppy here in the sense that really you could do that. You could take any denoiser. If you want to prove things about the variational approach, there are some restrictions. Yeah, you can't take any denoiser then. The other thing that also we have worked on, is still working on, is this idea of bi-level optimization. So here, this is maybe the most straightforward idea that one could have, and in particular because this is called optimal control. Also, this workshop, it's worth mentioning this too, because this is a kind of PDE constrained optimization idea. So here I say, okay, I have my variational problem. I parameterize my regularizer in whatever way I want to parameterize it. And then I come up with a good criterion for evaluating how good a solution of this variational problem is, a solution that now will depend on this parameterization lambda. And this is my evaluation criterion here. And then I want to choose a good parameterization lambda by minimizing the goodness, or by, I guess, maximizing the goodness of this solution U lambda of the variational approach. Okay, so this is called bi-level optimization because you have an optimization problem on 2 levels. Okay, so this is also super interesting, and I like this a lot. One thing to say about that is that the computational solution of these bi-level optimization approaches is not at all straightforward. They're super tough, and in particular with the type of parameterizations for regularizers that we have here that are, non-smoothness coupled with this very large dimensional problems is not is somehow one of the worst things that can happen. Yeah? So even if this is convex, even if the variational problem here is convex. Okay, so what do we do? So what we thought we could do is the following. Now, when you think about what a good regularizer is made of, or what a good regularizer should do, then on the one hand, a regularizer should suppress noise that is kind of characteristic for the inverse problem that you're trying to solve. And so here I don't just mean Gaussian noise or Poisson noise or whatever. What I mean is also the noise that is deterministic, that is generated by the inversion of the forward, by the ill-posedness of the forward operator, like these streak artifacts that we have seen with CT. Okay, so the regularizer should somehow suppress these. And so this is one heuristic. The other one is that I also want somehow that the regularizer pushes my solution U to my inverse problem closer to the ground truth. And so these 2 principles I now want to use to train the regularizer. And so how do I do this? So I create 3 distributions. And these will be the distributions these will be 3 different distributions of images or data that I will then use as a training set for training this regularizer. Okay. So the one distribution is maybe a kind of straightforward thing. I want ground truth images. I want examples of the type of images that the regularizer should like, that the regularizer should favor. Then I create another distribution of typical measurements that are taken of my inverse problem. Okay, typical measurements that are taken by the device that I want to solve my inverse problem of. And now these measurements I somehow want to turn back into images, okay, into typical images that I can now compare with the ground truth. And so to do that, I take samples from this distribution of measurements and I apply the pseudo inverse. So if assuming that I have a pseudo inverse for this problem, I apply the pseudo inverse to it and I create a new distribution Pn. So now the pseudo inverse, without explaining too much about it, in CT is just a filtered back projection. Okay, I'm just doing the most basic reconstruction that I know will show me all these typical kind of artifacts and characteristic noises of the inverse problem that I now also want to take into account when training the regularizer. So I call this Pn. And then the aim is to construct a regularizer that on the one hand aligns with the ground truth images, so that favors these ground truth images that come from PR. And on the other hand, suppresses the kind of characteristic noises that I see in the distribution Pn. So in pictures, very briefly, this looks like this. These are typical samples, let's say, of images, ground truth images PR that I want to reconstruct. These are typical measurements. And these are images that I reconstruct from these typical measurements via the filtered back projection. In this case, this is all CT. Yeah? So these are typical images that show us these characteristic noises that I want the regularizer to suppress. So Pn shows the bad guys, PR show the good guys, okay? And now I want to train the regularizer with these. In particular, I don't need this distribution anymore because the regularizer should act on images. So what I do is I train it with these two distributions. And because I trained it now distributionally, and you'll see this in a moment, this is actually also an unsupervised way of training because because I'm not going to compare them pairwise. I'm really going to compare distributions now. I don't need the ground truth to be paired with my measurements. And this is something that can be super handy when you solve inverse problems in practice. You don't need the ground truth to correspond to these measurements. The ground truth should just be something that is a good model for the type of solution you want to compute. Okay, and this links back to Yunan's talk in a way, because the Wasserstein distance appears again, but in this case, it's the one Wasserstein distance. So how do we do this? How do we train this regularizer? What is the criterion for optimizing the regularizer? And this is in our case now the Wasserstein distance, okay? So to do exactly what I said before is we are looking for a regularizer. So now F, or the maximizer of this will be my regularizer, F star. I'm modeling it as a one Lipschitz function that when I feed the regularizer F with samples from my noisy distribution from Pn, then the regularizer should be large, yeah, because it should not like this, right? I'm minimizing R. I'm minimizing F in this case. And if I feed it with samples from my distribution PR, then it should be small, okay? And F star is then my maximizer, okay? So let me just check. I have used 40 minutes already, right, Dejan? I have 5 more minutes or so.
You still have, right, 6 minutes or so, yeah.
Okay, super. So is this a good idea? Let me just briefly talk you why this might be a good idea to do something like this. Why could such a regularizer be might work in such a variational approach? So the one incentive, or the one yeah, let's call it incentive, is that if you look at samples from this noisy distribution Pn, okay, and you start with a sample from the noisy distribution Pn, and then you go a negative gradient step in the direction of the regularizer. So you minimize the regularizer, okay? You take a negative gradient step in the direction of so you take a step in the direction of the negative gradient of the regularizer, and you create a new distribution that I call P eta. Then somehow conceptually what you want to show is that the new distribution P eta is now better than the distribution Pn that you've started out with, right? Because you've minimized, or you've at least gone in a right direction with respect to F star. And this is indeed something that one can show. One can show that if you do this and you look at the Wasserstein distance between this new distribution P eta and the distribution PR, then you're actually decreasing. So what you show here is that this is actually going in a direction that decreases this Wasserstein distance between P eta and PR. So you're getting closer to your distribution of ground truth images. One issue, but I don't have time, is to iterate this argument. But this is at least the kind of first confirmation that this might be good. Another thing that is interesting is, if you do this and you make two more assumptions, if you allow me to make two more assumptions, I can tell you one more thing about the regularizer. One assumption is that your distribution of ground truth images, so this is called the data manifold assumption, that your distribution of ground truth images is supported on a compact manifold, on a weakly compact manifold. Okay, so it means that your distribution of ground truth images you have some control over. The other assumption you make is now about the distribution Pn in comparison with this distribution PR, and this is called the projection assumption. So you assume that you can recover the distribution of ground truth images by projecting Pn, the distribution of noisy images, onto the manifold, onto the data manifold M. So this is a kind of stronger assumption on the noise, in particular on the amount of noise that you have in your data, because this kind of you can think of as a low noise assumption. Okay, so if you accept both of these, then the additional thing you can show is, and this goes back to our heuristic that we want the regularizer to bring images close to the ground truths, is that the distance function to the data manifold is a maximizer of the Wasserstein loss. Okay, so a few kind of ideas of why this might work. Now, of course, we are not maximizing now over all one Lipschitz functions. So this is where the neural networks come in. So we are parametrizing now the Fs that I'm optimizing over by neural networks, just convolutional neural networks that are mapping an image of dimension n cross m to a real number, right? This real number should say how good this image is in terms of the regularizer. And then the one Wasserstein distance, I'm now also approximating. Not just that I now restrict the maximization to all from all one Lipschitz functions to these neural networks, but I also incorporate this one Lipschitz constraint here as a penalty term, as a Lagrangian. And then of course I have here only empirical distributions when I'm optimizing this. Okay, and then the summary is I'm training this by first training the regularizer, by first training the regularizer with this, the regularizer will be then psi theta. Theta are the parameters in the neural network. And once I've trained this, I plug it back in and solve my variational problem by, for instance, gradient descent. Okay. The good thing is, because I have a variational problem, I can now prove things about it. Of course, one issue here still is that this, if you don't do anything more, this is super non-convex. Huh? So is non-convex. Actually, I also can't assume that the regularizer is bounded from below. So the boundedness from below, I either get, so that the only thing I kind of assume here is that I have one Lipschitzness, at least approximately. And the other thing, so either I get the boundedness from below from the data discrepancy term, or I get the boundedness from below by adding something small to this non-convex regularizer, like an L2 squared or so. Anyway, so if I do this, then I can prove existence of this existence of minimizers. I can prove stability, but in the weak sequential sense. Yeah. Actually, there are counterexamples that you don't get norm stability, but this is what you can do. Yeah. So one thing we have done with Shubo recently is that we try to prove more about it by convexifying it. So you see the most successful regularizers in the literature have really been those which are convex. And so somehow convexity is so nice, it helps us so much in so many ways. So what we did is that we looked at the parametrization of the regularizer that has, on the one hand, this psi theta prime, which is again a neural network, but that we make sure is convex, and a little L2 squared term that now even gives us uniqueness, yeah, by strong convexity. Okay. So what we get is existence and uniqueness. If we use a regularizer like this, we get stability now also in norm. We get convergence in the sense that if I look at a sequence of regularized solutions and I let the regularization parameter go to 0 and the noise go to 0 with a particular rate, then I actually converge to the ground truth solution. And then because I have a convex problem that I now solve, I can actually also prove convergence for the method for a subgradient algorithm, in this case, for minimizing this functional in the end. I can tell you more about how you create this convex architecture, but this is actually super simple once you have looked at this. And now I'll show you some examples. So I'll show you two examples. Again, happy to tell you some more details about the training setup in a moment, but this is what you see. So I show you two examples. One is sparse view CT, which means low resolution in the angular sampling, but equidistant. Okay, and the other one is limited angle CT, where you have a whole wedge of angles missing. So here on the left, you see the ground truth. Here on the right, I always show you the reconstruction. So this is filtered back projection. Okay. And what you see here is the so-called PSNR. So this is a quality measure of how good this image is. The larger, the better. This is what you get with TV. This is what you get with another supervised deep learning approach for CT reconstruction. And this is what you get with the adversarial regularizer. So, and this is what you get with the convex adversarial. So the convex one was the one I like most because it's nice. You pay a little bit. You pay like 1 dB, well, actually more, 1.8 dB in terms of reconstruction quality, but you're still better than TV. Yeah? For limited view CT, actually convexity is not just nicer because of robustness. Well, actually the robustness comes back here, but also qualitatively it works better. This is filtered back projection. This is TV. This is this supervised deep learning approach. This is always the best one, of course, but this is supervised. And also they can't prove what we can prove. This is the adversarial regularizer. So this looks awful. And I can explain this also later. And this is the convex adversarial regularizer. So this definitely also gives you more stability. Okay, so takeaway messages. I really think that neural networks are a very powerful way to parameterize things that really historically we have proven that we can't really model very well, like the regularizer. It's really the right direction is when we combine data-driven approaches with rigorous mathematical methods. And there are many open questions. Yeah, so choice of optimality criteria for training such regularizers. Yeah, very often in applications, you're not reconstructing images for them to have a high PSNR, which basically means you want them to look pretty. But in particular, in medical imaging, you want them to quantify something, right? And so maybe you should take this also into account when training them. Uncertainty quantification with such learned regularizers would be really nice to do. And then interpretability is, of course, something that there is a huge gap between interpretability of total variation regularization and interpretability of this adversarial regularizer. So it would be nice to get a little bit closer. So I thank you very much for your attention. Thanks a lot. Thank you.
Thanks, Carola. This was very inspiring and very exciting. Are there questions? Again, you can just speak up as you would in a regular seminar, but if you prefer to send it in a chat, that's also fine.
I have a question. So it's a very nice idea. And I wonder how often do we need the training? So for example, you just said the CT data, some of the CT data miss some angle, and there will be another type of data have certain different characteristic of the. So do we do training all of them together, or we separate? This is the data that initially miss some angle, and this is the data that has some noise.
Yeah. Okay, so let me give you, actually at the moment, I can give you a bit of a sloppy answer if you allow, but soon there will be more because Sebastian is writing up his thesis and he has been tasked to do all these comparisons now. But so one answer is, of course, what we are learning is a prior. Yeah. So whatever we do, I mean, okay, the prior, the type of regularization, as you have seen, can screw up things pretty badly as well. But what is really important is that we will always stick to the forward model because we have this data discrepancy in the solution eventually. Yeah. So the only way the neural network acts here is to select. Yeah. So ideally to select if you choose this regularization parameter correctly. Now, how much does it depend how good, I mean, so this is a general thing, how good the regularizer is will always will always have an effect on the solution. Yeah? So better regularizers will always give you better solutions than not so good ones. So what does it take to learn a good regularizer that also you can move around also between slightly different settings? So what you can do is so they are translatable to a certain extent. Yeah. So you can, what Sebastian is actually, so that's why it's a kind of sloppy answer because I can't show you anything written because he's just writing it up. He has just shown this to me, is that if you change the noise level a little bit, yeah, then you can definitely train the regularizer on one noise level and then use it for another one because you can adjust this through this regularization parameter alpha. Now, if you train it for sparse angular sampling and then apply it to the limited angle problem, these are two very different inverse problems. And I told you that the way we train the regularizer is that we wanted to suppress the typical characteristic noises that the inverse problem gives you when you solve it. And so this will depend a lot on the forward operator. I mean, I want it to depend. So I'm training it because I'm training it in a way that I want it to depend on the forward operator. So yes, you need, for the particular problem you have in mind, you need to train it. Yeah. Yeah. That's, I guess, the message. Yeah. But you have a degree of freedom in how closely your forward operators are, of course. But I can't make this precise mathematically, I'm afraid. This is just empirical, yeah, empirical observations. Yeah.
Thanks a lot.
So, hi, Carola. How are you?
I'm fine, thank you.
Oh, thank you very much for your very nice presentation. Would you please go back 2 slides or one where you have the equation?
To which one?
Yeah, that one. The one that you showed to Jonah, where you have the regularization parameter.
Ah, yes, okay, yes.
And
this one, for instance.
Yes, that one. I'm just I have a question with regard to the optimization process, right? When you a nonlinear model, I mean a nonlinear mapping between your observations and the outputs, how your method perform, because you can have like multiple minima, right?
Yeah. Yes.
How
the
do
answer
you
is yes. That's
yes,
why I liked now our move to the convex setting. But yes.
But what kind of recommendations do you have if we face that situation in practice, for instance?
If you have a non-convex problem to solve?
Yes.
Okay, this is you can start a new lecture now, but yeah, I mean, okay, so my expertise is on local optimization methods, in the sense that so I mean, you could do simulated annealing or whatever to maybe find a global minimizer, but I think so. I mean, these optimal control problems that also feature in this workshop quite a bit, they are non-convex by nature if you solve something interesting. Yeah? And so I think people are usually happy in this context with local optima.
Yeah, I agree.
Yeah. And
no, but my point is that you will have different for different solutions. That's my point, right? I mean, if you have like a non-linear optimization, not convex optimization problem, you will get multiples alpha because you will have multiple solutions. So
yes,
I was wondering whether there is a way to, I don't know, place this information into your neural network and to get some extra insights. I mean, with regard to the solution and the variation of the alphas.
Okay, so here I'm not optimizing over alpha, right? I fix my alpha is fixed here when I solve it.
Yeah.
And then I optimize. If you want me to do something in the neural network to help this, then again, I'm telling you about the convex neural network.
Okay.
I think that. But the other thing is, of course, initialization matters if you solve a non-convex problem. So something that that you can do is optimize with something. I mean, initialize with something that you already think is kind of okay-ish.
Yeah.
So either
like a background information. Yes, I
use or a simple reconstruction. Initialize with a simple reconstruction. Yeah.
Okay.
But yeah, this is definitely an issue. That's also why in the slides where I showed you the zoo of regularizers, these were all convex regularizers.
I see. Yeah.
So, yeah.
Okay. Thank you.
No, thank you for the question.
Can I follow up with that? Hi, Carola.
Hey, Stacy.
How are you?
Fine, thank you.
Lovely talk. Thank you. Following up on Yunan and Elias's question, because you had mentioned that there's different kinds of noise in these applications, and you're tackling that with T, but which of course makes the world a lot worse by even mentioning this. But you have this, of course, L2 fidelity term, which is strictly convex and works very nicely for certain types of noise. Does the type of noise with different applications, have you tried anything where that's particularly problematic, where you need to consider even convex, maybe not strictly convex fidelity terms, or learning that in any way?
So yes, so one thing maybe to say, so this is thanks a lot, Stacy, for this question. So in a way, we are taking, even when we train the regularizer, also the noise distribution into account, because we train the regularizer with this distribution Pn, right? That features at least the inverted noise, right? The other thing is that you can and then when training the regularizer, you could take also Poisson measurements, for instance, and train the regularizer with those, and then have here instead of the L2 Kullback-Leibler divergence or something like this. So I think this is a very good suggestion. Something that we have done, but not in the context of the adversarial regularizer, is that but in the context of bi-level optimization, is that we try to learn the data discrepancy. Because sometimes also the noise distribution itself is not straightforward to model by one or the other distribution. Yeah.
Yeah, thank you.
I don't know if this answers your question, Stacy, but that's because it's not one perfect answer. It's two answers in two directions. But
no,
yeah.
No, that makes sense. Thank you.
Mm-hmm.
I had one question. For this to work well, somehow you need to have enough, and it seems intuitively like the right thing to do, I really have to say. But you need to have enough samples of the ground truth measure compared to the complexity of the data you are trying to recover, right? Of the images you're trying to. How do you know, basically whether you have enough ground truth images, both, practically and theoretically, kind of, how does this, does this have to scale with noise, or in which way? What is telling you if you have enough data?
I don't know. No, this is a really difficult question, and it's a very, very important question. But this is something that I really don't know. I would love to show something like this, but I don't know. Practically, I can tell you practically, we again, practically what I showed you now, we've trained on lung CT data, and then we test on lung CT data. Sebastian, makes sense somehow. But what Sebastian is at the moment trying is what happens if you train on CT of the knee, yeah, and then apply it to lung, or what happens if you train on knees and lungs and then apply it to. So how? But this is all empirical at the moment exploration, because I don't know. Yeah, because I think we first need to get some intuition for what works.
Right.
Yeah.
Right. And just one other question, which is somewhat related and also is related to Yunnan somehow talk, right? So when you, if I understood correctly, right? So somehow the words, if you could recover perfectly the manifold, right, then your adversary is really the distance to the manifold, right? But when you measure,
at least this is also, so the yes and no, because where is it? Here, you're right. So because again, this is a maximizer to this Wasserstein loss, right?
Right.
Yeah.
Right, but what I was just thinking, right, so somehow using a different metric, right, other than Wasserstein, or using a different way would result in a different kind of
yes.
Right.
Yes. So in the context of of regularizers, actually we have not done this, but Sebastian has written a paper with another PhD student like two years ago or something like this, where they looked at Wasserstein distances with different metrics, and so with different LPs. And they have seen a difference, but they have looked at these generative adversarial network trainings with these Wasserstein losses. So we have not looked at this for training the regularizer, but I agree it could be interesting. Yeah, because this gives you the metric of really the metric on the images, right? So it could be interesting to look at something else. Yes.
Thanks. So I'll share again we can continue discussing in the Gather Town, right? So we can switch there. Let me share the link. Let me just pick it up from again from Daniel's email, right? So okay, sorry. So I'll switch there myself. I'll just somehow remind everyone we continue in 45 minutes, right? So we'll have some discussion, then a little bit of a lunch or dinner break, depending on where you are, and then we'll continue in 45 minutes, right? So hope to see you in Gather Town in the meantime.